Welcome to the Explainer. Today, we are diving deep into the science behind something that drives us all crazy, that mysteriously fading wireless signal. We're going to break down the core ideas from Andrea Goldsmith's classic book, Wireless Communications, to really get what's going on between your phone and the cell tower. You know the feeling, right? We've all asked these questions, whether it's about our Wi-Fi, our cell service, or pretty much any wireless connection. And the answer isn't just one simple thing. Turns out it's this really fascinating mix of predictable physics and just random chance that decides how radio waves make their way through our very messy world. Okay, let's get into it. So, here's our game plan. We're going to follow the journey of a single radio signal. First, we'll define the problem, then we'll imagine a perfect world for that signal to travel in. After that, we'll start adding back all the real-world stuff, like walls and buildings, to see how engineers actually model all this chaos and, figure out if you're going to have a good connection or not.
All right, so to kick things off, you've got to understand that a wireless signal is getting pushed and pulled by three different forces, and each one works on a totally different scale. You've got path loss over really long distances, then shadowing over medium distances, and finally something called multipath fading that can literally change if you just move your head. For today, we're going to focus on the two big ones, path loss and shadowing.
Here's a good way to think about it. Path loss is like a predictable trend. The signal always gets weaker the further you get from the source. But shadowing, that's the random up and down variation around that trend, like when you walk behind a huge building. Getting a handle on these two different effects is absolutely the key to designing the reliable wireless systems we all use every single day. So let's start with a little thought experiment. Let's just strip away all the complexity of the real world. Imagine a single transmitter sending a signal through a perfect vacuum. I mean, completely empty space, no buildings, no ground, nothing to get in the way. What happens to the signal then? Well, even in this perfect, empty world, the signal still gets weaker. This is what we call path loss. Honestly, the easiest way to picture it is to think of a light bulb in a pitch-black room. The light is super bright right next to the bulb, but it gets dimmer and dimmer the further away you get. Radio waves work in the exact same way. And here's the really crucial idea. The transmitter sends out a fixed, finite amount of energy. As that radio wave travels out, that same amount of energy has to spread itself over the surface of a bubble that's constantly getting bigger. It's kind of like trying to spread the same small amount of butter over a bigger and bigger piece of toast. The layer of butter just gets thinner and thinner, right? The total amount of energy is the same, but its concentration at any one point gets a lot smaller. And this brings us to a fundamental law of physics, the inverse square law. It sounds complicated, but it's not. It just means the power your phone receives goes down with the square of the distance. So if you double your distance from the tower, you don't get half the power. No, you only get 1/4 of the power. This predictable weakening, this free space path loss, is the absolute baseline for every single wireless model out there. Okay, so a perfect vacuum is a nice, clean starting point, but let's be real, our world is anything but empty. So let's add our very first and probably most important real-world complication, the ground. All of a sudden, our nice, simple signal has more than one way to get to where it's going. Yeah, your phone isn't just picking up the signal that took the straight line path from the transmitter, it's also picking up a copy, or maybe several copies of that signal that bounced off the ground, or a nearby wall, or another building. This creates multiple paths, and trust me, things get really interesting when these different paths all show up at your phone at the same time. To deal with this, engineers use a really simple but powerful tool called the two-ray model. It does what it says on the tin. It calculates signal strength by looking at both the direct path and one reflected path. But the really cool part isn't the model itself, it's what happens when those two signals actually combine at your device. See, if the peaks of the two waves arrive at the same time, they add up, they reinforce each other, and you get a stronger signal. That's constructive interference. But, and this is a big but, if the peak of one wave arrives at the same time as the valley of the other, they cancel each other out, and your signal gets way, way weaker. That's destructive interference, and that is exactly why moving your phone just a few inches can sometimes take you from full bars to absolutely no signal at all. The two-ray model is a great step up, for sure, but a modern city is, well, it's a lot more than just a flat plane, right? It's this chaotic jumble of buildings and cars and trees. So how on earth do engineers even begin to model something that complicated? Well, there are basically two main approaches. The first is what we call deterministic, like a technique called ray tracing. This is basically a brute force method where a supercomputer tries to calculate every single possible path a signal could take, bouncing off buildings, bending around corners, the whole shebang. It's incredibly accurate, but it needs a perfect 3D math and just a ton of processing power. For planning a whole citywide network, it's usually just not practical. So, a lot of the time, engineers turn to the second approach, empirical models. You can think of these as really sophisticated scientific rules of thumb. Basically, researchers went out and took thousands and thousands of signal measurements in all kinds of different places, dense cities, wide open suburbs, inside office buildings, and then they came up with mathematical formulas that just fit that real world data. Models like the Hada model are just incredibly useful. They give network planners a fast and, a reasonably accurate way to estimate the average signal loss over a big area without having to map out every single building. They might not be perfect for predicting the signal at one specific spot on the sidewalk, but for designing a huge cellular network, they are an absolutely essential tool. And the same idea applies indoors, which, as you can imagine, is critical for Wi-Fi. Indoor models start with a basic formula and then just add penalties or attenuation factors for every single thing this signal has to punch through. This is exactly why your signal is amazing in the living room, but basically dies once it has to go through a couple of walls to get to your bedroom. Okay, so up to now, we've mostly talked about path loss, that predictable average drop in signal strength over distance. But we all know from experience that the real world isn't about averages. There's another, much more random factor at play. Think about it. If you were to walk in a perfect circle around a cell tower, keeping your distance exactly the same, a path loss model would say your signal should be perfectly constant. But that's not true, right? Your signal bars would be jumping all over the place. These variations, these ups and downs, are caused by big objects that get in the way and cast what we call a radio shadow. And this phenomenon has a name, shadow fading, or just shadowing. It's the reason your signal might be awesome on a street corner where you can see the tower, but then terrible just one block over behind a big skyscraper. You've literally walked into an invisible shadow where the radio waves just can't reach as well. Now, the really fascinating part is how engineers model this randomness. Obviously, they can't predict where every single shadow is going to be, but from taking countless measurements, they've found that these signal variations follow a very consistent statistical pattern, a bell curve. This means that while they can't tell you the exact signal you'll get at one specific spot, they can calculate the probability of the signal being strong or weak in that general area. This quote really highlights a key property of shadowing. Unlike those super fast fluctuations from interference, which can change if you move your phone just a few inches, shadowing changes over a much bigger area. Engineers call this the decorrelation distance. It's basically how far you have to move for the signal to be blocked by a totally different set of stuff, which is usually around 10 to 20 meters in a typical city. So we've got these two main forces duking it out, the predictable decay from path loss and these random, large-scale fluctuations from shadowing. So how do engineers put these two powerful ideas together to build a network that actually works for millions of us? They follow a really clear, logical process. First, they use a path loss model to figure out the average signal strength they can expect across a whole area. Then, they layered the statistical randomness of shadowing right on top of that average. This combined model gives them a way more realistic picture of how the signal will actually behave. And from this, they can calculate two absolutely critical numbers. The first one is outage probability. For any given spot on the map, they can now ask, what are the odds that, because of the distance and because you might be in a radio shadow, the signal here will be too weak to make a call or stream a video? A carrier might aim for something like a 2% chance of that happening at the very edge of a cell. And that leads directly to the second number, the cell coverage area. This is really the end goal of all this modeling. By mapping out all the locations where that outage probability is acceptably low, they can literally draw the boundary of a cell on a map. This is how carriers make those coverage maps you see in their commercials, and it's what tells them where they need to build their next tower. So when you think about it, the next time your signal fades, it's almost always a combination of both of these things. You're far enough away for this signal to be weak on average, and you've probably just stepped into a spot where a big building or a hill is making things even worse. And now you have a much better idea of the fundamental forces, path loss, and shadowing that engineers are battling every single day just to keep us all connected. Hey, if you found this breakdown helpful, do us a favor and hit the like button and subscribe to the channel. Your support really does help us tackle more complex topics just like this one. And of course,
If you have any questions or have a great idea for our next explainer, please let us know down in the comments. We'd love to hear from you. Thanks for watching.